the first realization that there were actually distinct layers of the Earth came from this guy right over here, Andrija Mohorovičić. And I apologize ahead of time to any Croatians for butchering any of the pronunciation. And he was a meteorologist and a seismologist, and he was the first one to notice in 1909 when there was an earthquake. There was an earthquake in Croatia, a little bit southeast of Zagreb. So the earthquake was roughly over here. And lucky for him and lucky for us, before that earthquake, there was actually a bunch of seismographic stations already in the area. And all these seismographic stations are they essentially, instruments were installed so that if there was any essentially seismic waves passing, they would be able to measure it when the waves got there. And what was interesting about this, Andrija realized that if you had if the entire Earth was just kind of a uniform material, so let's draw that scenario, it would get denser as you go down, and so you would have kind of this refraction, this continuous refraction, or these curved paths happening. But he realized that, let's say we had an earthquake right over here. So this is the uniform case. Uniform layer. Only one layer, although it does get denser. Then the closer you are to the earthquake, so waves would get there first, then waves would get over there, then waves would get over there. And these are the body waves. These are the ones that are traveling through the Earth's crust. But in general, the further you are away from the earthquake, or the time it takes for the waves to get to a point, is going to be proportional to the distance that point is away from the earthquake. So you would expect to see something like this. So if you were to plot on the horizontal axis, if you were to plot distance, and on the vertical axis you were to plot time, you should see something like this. You should see a straight line. And that's just because it's traveling roughly the same velocity along any of these arcs. It's maybe getting a little bit faster as it's getting deeper, but roughly the same velocity is traveling along these arcs. And the distance of these arcs are proportional to the distance along the surface. So essentially, the time is they're all traveling roughly at the same velocity, and they're just traveling different distances. So the time it takes is just going to be proportional to the distance. But he noticed something interesting. When he actually measured when the waves from that earthquake reached different seismographic stations, he saw something interesting. So this is the theoretical if we had a kind of this uniform one-layered Earth. But he saw something interesting. So once again, this is distance, and this right over here is time. And at 200 kilometers away from the earthquake. So until 200 kilometers, he saw exactly what you would expect from a uniform Earth. It was just the time was proportional to the distance. But at 200 kilometers, he saw something interesting. All of a sudden, the waves were reaching there faster. The slope of this line changed. It took less time for each incremental distance. So for some reason, the waves that were going at these farther stations, the stations that were more than 200 kilometers away, the stations, somehow they were accelerated. Somehow they were able to move faster. And he's the one that realized that this was because the waves that were getting to these further stations must have traveled through a more dense layer of the Earth. So let's just think about it. So if we have a more dense layer, it will fit this information right over here. So if we have a layer like this, which we now know to be the crust, and then you have a denser layer, which we now know to be the mantle, then what you would have is, so you have your earthquake right over here. They're closer by while you're still within the crust. It would be proportional. And then let's say that this right here is 200 kilometers away. But then if you go any further, the waves would have to travel. So they would go like this. And then they would get refracted even harder. So they would be a little bit curved ahead of time. But then they're going into a much denser material, or it's not gradually dense. It's actually kind of all of a sudden a considerably more dense material. So it'll get refracted even more. And then it'll go over here. And since it was able to travel all of this distance in a denser material, it would have traveled faster along this path. And so it would get to this distance on the surface that's more than 200 kilometers away. It would get there faster. And so he said that there must be a denser layer that those waves are traveling through, which we now know to be the mantle. And the boundary between what we now know to be the crust And this denser layer, which is we now know to be the mantle, is actually named after him. It's called the Mohorovičić discontinuity. And sometimes it's just called the MOHO for short. So that boundary between the cusp and the mantle is now named for him. But this was a huge discovery because not only was he able to tell us based on the data, based on kind of indirect data, just based on earthquakes happening and measuring when the earthquakes reach different points of the Earth, that there probably is a denser layer. And if you do the math, under continental crust, that denser layer is about 35 kilometers down. He was able to tell us that there is that layer, but even more importantly, he was able to give the clue that just using information from earthquakes, we could essentially figure out the actual composition of the Earth, because no one has ever dug that deep. No one has ever dug into the mantle, much less the outer core or the inner core. In the next few videos, we're going to kind of take this insight that we can use information from earthquakes to actually think about how we know that there is an outer liquid core and that there's an inner core as well. And then obviously you could keep going and think about all of the different densities within the mantle and all of that. I won't go into that much detail, but I'll see you in the next video.